Afternoon, everybody.
Hey, Mr. Peterson, Jack Frost nipping at your nose?
Yeah. Now let's get Joe Beer nipping at my liver, huh?
Sometimes you wanna go where everybody knows your name.
A norm is represented by two bars on either side of the given vector, in this instance x. The most commonly recognized norm is that of Euclidean space, known as the L norm. For any vector in Rn, this norm is the square root of the sum of the squares of each element in that vector. This should be familiar. In 2- and 3-dimensional space, this is exactly the same as taking the hypotenuse or diagonal. L norms also exist in the vector space Cn. Here, the norm equals the square root of the sum of the products of each element and its complex conjugate. In order for a norm to be valid, it must satisfy the three properties shown here. In order to demonstrate these properties, we have created a simple example in R2.
When Norm enters the bar, he typically stops at the coat rack before heading to the bar. Today, Norm is curious how much shorter his walk can be if he goes directly to the bar without removing his coat. He defines himself as the origin and uses norms to satisfy his curiosity. First, Norm stands at the door and considers the bar. He knows that it is at 11.3 with respect to his position by the door and calculates the distance by taking the norm to the bar. Next, Norm considers the coat rack. He knows that it is at 1.2 relative to his position and calculates the distance by taking the norm to the coat rack. Afterward, he walks to the coat rack and considers the bar again. The bar is now at 10.1 with respect to norm, and he takes another norm to find the new distance. Adding these together, his typical walking distance is about 12.3 yards. Finally, Norm compares the two routes and finds that his walking distance will be about 1 yard shorter when going straight to the bar. With that, the triangle inequality property is satisfied. Good job, Norm. You deserve a beer.
To test the second property, Norm considers the distance between him and the bar. Norm knows the location of the bar in yards, or 11.3, and from his previous calculations, the distance it takes to walk to the bar, or 11.4 yards. Norm believes that there are 3 feet in a yard, so the coordinates of the bar in feet should be 3 times 11.3, or 33.9. He wants to check that the distance to the bar in feet is simply 3 times the distance in yards, so he uses his feet to check, assuming each foot is 1 foot long. It takes Norm 3 times the norm of 11.3, or 34.2 feet lengths to get to the bar when he places 1 foot after the other, or 3 times the original distance in yards. To check that this distance is the same as the calculated distance from the coordinates in feet, Norm takes the norm of the coordinates in feet, or norm of 3 times 11.3, equal to the norm of 33.9, which is also equal to 34.2 feet. Since the two distances are equal, the second property is satisfied, and Norm concludes that his feet are in fact 12 inches long.
Norm's third test examines the final property of norms. If a norm equals 0, the vector which produced that norm must also equal 0. In Norm's case, the only way he will be at his stool at the bar is if the distance between himself and the bar is 0. If the distance does not equal 0, it is not possible for Norm to be at the bar.
Sometimes you wanna go where everybody knows your name, and they're all